Hello, everyone. This week we will be focusing on something else than most of the time. Up to this point, up to last week, we have designed PID controllers, but now we'll use a controller. We'll design it again, but that's not the focus of today. We'll try to put on some constraints about our control signal. And this is a practical thing most of the time in real-world applications. It is not really possible to use the control signal without any limitation. So, for example, if we have a car and we are driving a car, then we can only get to a certain speed limit. For example, we have the top speed of a vehicle. So we cannot apply more speed, or we cannot have a higher speed than the top speed while driving a vehicle. So if you are, for example, looking for the position control of such a vehicle, then there will be a limited speed. So if your control signal is the speed, then you will have a limit for it. The same applies for other type of systems. One of them could be the acceleration limit, again, on the vehicle, or you might have a voltage limit or a current limit. So what if we have a certain limit on our control signal? Now, up to this point, we've used linear systems. Therefore, the implication was that if I have a relation between output and input, I can apply infinite input and get infinite output, which is not possible in the real world. So today will be all about this limitation, or saturation in other words. So we'll use a saturation on our control signal. Before we transition into that, we'll design an API controller where the settling time and rise time are given. And then we'll look at the control signal, and then we'll apply a limit between 0.7 and a negative 0.7. And we'll see what the effects will be and how can we maybe deal with some problems that could arise here. So let's start by designing the API controller. Now, I've mentioned about the rise time and peak time previously. So I'm just going to show you the first part because that's not really the focus here. So we have the settling time formula. Maybe I might zoom in a little bit. So we have the settling time formula, which is already well known. And here's the typo. Here should be a plus here, 2.5 times zeta plus 0.8. And then this is the rise time formula, the first order approximation of the rise time formula. So you can see that we have a common term omega n. So what I can do is I can maybe ratio them. So Ts divided by Tr would be 4 divided by zeta omega n divided by this expression here. And I'll most probably cancel out omega n here. And then I'll get something depending on zeta, and I can solve that. So what I'm trying to say is that we have 4 divided by zeta omega n, and then this expression here. What if I, for example, leave omega n here and plug it in here, or if I'm just ratioing them? Then we have Tr equals 2.5 zeta squared plus 0.8 zeta divided by 4 Ts. So if I arrange this, I'll get a second order equation here. So it's really easy to solve this because this is a second order equation, and I know what Tr is and Ts is, and I'm looking for zeta. So basically I can work out what zeta is based on the settling time and rise time. So that's the first step. And then I can get that zeta and use any of these two relations here again, and then look what omega n is. So basically, I've again shown you that given two time domain specifications, it is possible to work out what zeta and omega n should be. So let's do that. I have already defined rise time and settling time requirements here, and we have the transfer function. So the equation was to look for 2.5 times zeta squared plus and 0.8 times zeta. What else do we have? Minus 4 times Tr divided by Ts. So I'm looking for the root of this. You can maybe use the symbolic engine here, define zeta real, and then try to solve that. But I'd not go that way. I'll just use the roots command. And using this command, I can just give the coefficients. And I know that the coefficient here is 2.5. And then we have 0.8. And then minus 4 times TR divided by TS. So there we go. By the way, you can also work your way out furthermore here instead of this equation, because we can see that they will have the same sign, or zeta 1 plus zeta 2 should be negative here. And then zeta 1 times zeta 2 should also be negative. So you can conclude that there will be a negative zeta 1 and a positive one, and we are interested in a positive one. So you can maybe also try to use this, but it's not really that big of a deal, since we can use just directly roots here. And let's say zeta val equals this, and then see what zeta val is here. So let's run it. Now we can see that we have one negative value and one positive one. So we're going to choose this positive one, which is fairly easy. Zeta val positive. Is there a typo? Yep. Zeta val. There we go. Now we know what zeta is, so we can just use the settling time here. So omega n val, or maybe I should call it zeta and omega n. There we go. Should be equal to 4 divided by Ts times zeta here. So I know what zeta and omega n should be. So let's go back to our question here. Design a PI controller. So let's try to do that. We have a second order open loop. Using a PI controller, we'll have a third order one. So let's define sims s. Here. And this would be 4t divided by s squared plus 15 times s plus 20. There we go. Now let's define PDS, which is s squared plus 2 times zeta times omega n times s plus omega n squared. Now let's define the residue pole here. ES, S plus P, and then the polynomial, or let's maybe also define KP and KI, which are also real. And then the controller, KP plus KI divided by S, and then closed loop. There we go. And then PZS, PCS, non-then. Now here we should again take the coefficients of PCS and normalize them. We get all the coefficients, and then all equals all divided by the first element, which is the highest order S term. And then the problem is to take the coefficients, or let's say pole equals coefs of PDS times PS, all equals solve the problem and see what the solution looks like. Hope that we didn't forget anything. So let's see. There we go. So sol.kp is this, sol.ki, and sol.p. There we go. Now we can see that there are positive values, so therefore I can see that P is positive, therefore we have a stable closed loop, and then we have also KP and KI values. So let's define our controller, or let's say KP val is equal to double sol of KP and Ki. Controller is Kp Ki. Feedback ts, 1, and info, step info. Let's get the step response. Let's create a figure. Let's plot t, y. There we go. So, of course, we've used the symbolic ones, so this should be Kp val and Ki val. There we go. Now, as you can see, we have the step response. Of course, we have to look at the step info here. So we have rise time 0.2 and then settling time 1.8. So yeah, it is working. You can see that the time domain specifications are met. Of course, there's a bit difference in the rise time, but yeah, seems not to be a big deal. We can also look for ZVKTS in order to determine where the zero is. So we can see that we have a real value 2.22 here roughly. And then there's this here 5, so 2.5 times dominance. And then there's a pole at 10. Not the ideal setup here, of course. We'd like to have this zero further away, but this still works because we have a certain dominance factor between the dominant poles and the zero here. That seems to be working. So, of course, this part is not really the focus of today. The first question is to design a PI type controller, which we've done already. But the second question here is to look at the control signal. So, and let me remind you that the control signal is the following. We have a summation point here, we have the controller, we have the system, and then there's this feedback here. There we go. Something like this. So now here we have the reference. Here's the output. And here we have the difference between the reference and the output. And of course, the output of the controller is the control signal. So this is the signal that controls the system, that tries to change the behavior of the system. Therefore, what we are needing here is to look at U here. So we need to determine U. Now, of course, you can go ahead and use Simulink, just drag and drop some transfer functions and build this feedback loop. And you can maybe also connect a scope at this point, and then you'll see what the control input is. But it is also possible to use MATLAB itself without opening Simulink. And the question here is the following. How can we use the step function here in order to determine the control signal? Or we can also, by the way, obtain E here, the error here. It's also possible to use step for that. So do you have any idea how we could do this? How can we determine U here using step? So what I really want to do is I'm just going to look for UT here. And then, of course, I need a transfer function for that. What is TU here? Any ideas? Because this is the most crucial part. Gain derken?
Katsayısı step'e verdiğimiz, biri oturmasını istiyorsak biri veriyoruz. Ama oturmasını istiyorsak puan veriyoruz.
O ama referans. Şuradaki R'ye veriyoruz biz onu. Kontrolör KP ve KI'yi kullanarak ne üretiyor ona bakmak istiyoruz şu an. Dolayısıyla muhtemelen sabit bir sayı değildir. Dinamik bir kontrolörümüz var çünkü. Çünkü dikkat edersen şurada kontrolör var. İçinde integratör var, yani şu şekilde. Kp artı ki bölü s gibi bir şey var. Burada transfer fonksiyonu var. Bir şeyin integralini alıyor, oranını alıyor, topluyor. Aslında bunun çıkışı ne? Onu görmek istiyoruz burada. So, yeah, we have a dynamic controller, which means that it's nothing constant here. Well, eventually maybe it's constant, but during the transients, we'll have dynamic behavior. And the transfer function of the controller, since we are using a PI controller, is Kp plus Ki divided by S. So what does this produce, basically, is the question here. So any ideas? How can we determine, or what is the transfer function Tu here? Şimdi kazancımız yok ama. Şimdi PID bir kontrolörle çalışıyorsak dediğin doğru. Ama elimizde bir dinamik kontrolör var. PI kontrolör var. O yüzden bu biraz problematik bir şey. Çünkü zamana göre değişiyor çıkışı. Yani zamana göre değişmesinin sebebi integratör var içinde. Referansa ulaşırız. Kapalı çevrim olduğu için şu an elimizde. Yani şurada ne yapmam gerektiğini söyle, onu yapayım ya da. Mesela TS'i mi çarpacağız bir şeyle? Y bölü GS diyorsun. Şu şekilde. Tamam. Peki nasıl tanımlayacağım şu an ben Y bölü GS'i? Dolayısıyla şu GS diyorsun, şunların yanına gelecek mi? Şöyle bir şey mi olacak? Ya da yukarıdakini götüreceğiz. Şöyle. Now the suggestion was to go inverse because we know what the relation between y and r is in the closed loop, namely fsgs divided by 1 plus fsgs. What if we divide by gs, because we know that the relation here is that we have gs times u here. So I know the relation between y and r. So what if I plug it in? Fs times gs divided by 1 plus fs times gs times r. This is basically our relation in the closed loop. So if we plug this in order to do that, we have to just use this here. Or in other words, we have to look for u here. So the inverse relation here. So u is equal to y divided by gs here. Therefore, we have to plug this in and divide by gs in order to obtain the control transfer function, control signal transfer function. Now, this is a way of thinking, but what I would rather do is the following. Since we have a connection here, we can just take this gs here. Since this is not our output anymore, we have to put it down here. Hope that I can do this. So we're just moving this here. Therefore, we have the signal y down here. So I did not change anything here. If you look at this summation point here, you have r, and then we have y, and then r minus y gives us e, and e times fs gives us u, and again u is the output input of gs. So therefore, this is basically the same block diagram as the previous one here. And if you look at this, you can basically see. Let me just move this a little bit to the right. You can basically see that we know this transfer function here, because this is now fs divided by 1 plus f times g. So you can also directly conclude that by manipulating the block diagram here. So by this way of thinking, it's also possible to do the following. So if I'm interested in E here, what I can do is I can also move this one here, down here. Just basic block diagram manipulations. So then we'll have U here, and then E here, where the output is also E here. So, and you can see that, again, nothing changed. I have E here. E times Fs should give me the control signal. The control signal is applied to the system. I get the system output, and I take the difference between the reference and the system output, and I generate E again. So these three block diagrams are basically the same. The only difference is that we are basically interpreting the output a bit different here. Here, the output is Y, the system output, the actual system output. Here, the control signal. Here, the error. And here I can also see that for the error, I have just gain 1 here. So the transfer function of this here should be 1 divided by, and then the loop f times g. So 1 divided by 1 plus fg. Or, as your friend suggested, we can also divide by fs to get, again, the same effect. So, therefore, if we take these closed loop transfer functions and define them and use the step function here, we should get basically the error, the control signal, and the output simultaneously for the same system and the same setup here. So let's do that. We have this here. I can just use the feedback command. And I can say that I have only Fs, and Gs is in the feedback. Therefore, I'll get Tu here. So let me also, by the way, pass in T here to have same time vectors. And then let's look for Te, which has gain 1, and then Fs times Yes. Now let me change this to a subplot. Let's have 3 rows, 1 column, the first one. And let's start with the error here. Now, TE, let's repeat this. Control signal, and then the output itself. 3 and 2. Let me comment these out. Yeah. Of course, titles are not correct. Let me change that. There we go. Now we can see what the error is versus time. We have the control signal and we have the output. Now for this system and this controller, for our setup here, we can see that initially the controller applies 1.5 to the system. And the reason there is probably KP val, KI val. There we go. Now, do you see the connection here? Why is the initial control signal gain or value equal to 1.5? And remember that it was a combination of KP val times the error plus KI val times the integral of the error. So shouldn't it be a greater value where the result is not really a greater value? It's 1.52 here. Do you see the reasoning here? Why? Tabii. Şimdi kontrol işaretinin ilk andaki değerine bakıyoruz. T0'da 1.5 civarında bir şey. Fakat kontrolör katsayılarına bakıyoruz. 1.5'lik bir KP kısmı var. Ama tek KI kısmı var 8.99. Şimdi bunların bir kombinasyonu olan çıkış kontrol işareti ise eğer, neden 1,5 civarında daha yüksek bir değerde değil?
İntegrasyon sıradan başka bir şey yok mu?
Sen de mi diyeceksin? Now, I just repeated the question in Turkish, and here we can see that at initial time t equals 0, the integral output is basically 0 because we have not started to sum up all the errors or versus time because we are t equals 0 at t equals 0. So the integral of this here at the initial time step here is equal to 0. Therefore, the p-type, it's kind of a p-type controller at t equals 0. Of course, one sample, if we pass one sample, we see that it is growing here because we have 1.66 and the error is going down. So Kp times 1 should give us only 1.52, whereas the control signal is increasing because we have this integrator and it is giving an output other than 0. And as time passes, we can see that the control signal goes down. But somewhere here, we have an important point here because approximately this point here shows us something special. Now, what is this point? Look at the title here, and it is equal to almost 0. So at this time instance, at 0.28, we reached our actual reference signal in the output. But since we are still applying a certain control signal, we have an overshoot here. The control signal goes down in magnitude. At this point, we are almost applying nothing here. But then we still have some error left here. So therefore, then the integrator will apply something. Therefore, it goes up here a little bit, and then goes down and up and down, and then this settles down to a certain value, which means that we have reached a steady state here at the end. And you can see that the error value here is tending to 0. It's almost equal to 0. Now, and you can see that the peak value here is 2.02. So you need this much control signal at its peak in order to control the system. So what we want to experiment with here is to limit this control signal. So we need to limit this control signal to 0.7, something like this here. It should never surpass this limit here. Also in the negative one, but we don't have any negative control signal. So first of all, technically, how can we achieve this? So that's the first part we need to deal with. And then we'll see what really happens here. Now, if we're using MATLAB here, it's not quite easy to use a saturation element or to limit the control signal because we are not basically accessing the internals here. We separately simulate what should happen over and over again. For example, we have the closed loop here. We simulate that. We don't get the control signal because it's in the internals. We don't get the error. We just recalculate it here. So we should basically change our algorithm or code here in order to get the internal values of a certain closed loop structure. So that's the first step. Again, you can use Simulink, but I'll use something different in order to showcase that it is possible to use MATLAB like that. And it might be a bit more advantageous in that case. We'll see and talk about that. So in order to do such a thing, we need to use the MATLAB and the fact that we can basically simulate control systems using just plain difference equations. So let me start on this, and let me also remind you that in terms of coding, you don't really have to follow this. Just sit back, relax, and see what we are trying to do here. The basic concept is important here, not the code, because you will not be responsible of this code, because it's a bit messy, and you'll see why. Now, first of all, we can use this transfer function here and convert this into a state space realization. We'll do that. And then we'll just discretize it in order to use difference equations, and then code it so that we have basically a discrete simulation here, and then we'll implement our controller and have the closed loop. Since we are doing everything manually, we'll have full control over the whole feedback structure, because we'll generate the error ourselves, the integrator ourselves, everything. So, and I'm not going to use this part here. I just need the transfer function itself. Now, usually you can also use pen and paper to convert it to state space, but that's again not the case here, because it's not the focus of this discussion. So first, let's say TF to SS, there's such a code function that converts the transfer function object into an SS object. And let me show you how it's used. Now, you can see that it gives us 4 matrices, and I'm going to show you what those are. So let's again go back here. Now, we want to have a model that looks like this. If you don't know anything about state space, this is the only thing that you need for today. Y equals C times X plus DU. So this format will help us in order to simulate the whole system. If we somehow convert this transfer function into this notation, then we can do the following. Now, since we are going to solve it numerically, instead of using a continuous time derivative, what we'll do is we will use delta x divided by delta t. So the change in x divided by the change in t. Since we will also work in discrete time, we will have a sampling time here. Call it ts, call it tau, whatever we want. Let's call it tau. We need a certain sampling time because we will use a sampled data here. So if we have that, then what we can do is instead of delta x, we can use xk minus 1. Because this is a difference here, divided by tk minus 1. Of course, tk minus 1 has a special meaning because it is the difference between two-time instances, consecutive two-time instances, which is already by definition the sampling time. So therefore, we have the sampling time here, or tau, as we've called it. And we can use this approximation. This is not actually equal. This is approximately equal, by the way. Not this one, but this one here. This is not exactly equal. This is approximately equal. Let's call it that. There are some constraints on this. One of them is that the sampling time should basically tend to 0. That will give us the definition of the derivative, the geometric interpretation. But that's not possible, so let's pick just a very small sampling time. That will be our solution to this. Now, if we have this, I'll just define it like this. And since, for example, y equals cx plus du is just a static relation, what I can do is I can just evaluate this at a certain time instance. Let's call it k minus 1. So this will be c times x k minus 1. This will be d times u at k minus 1. This will give me y at k minus 1 because this is a static relation. Now, I'm also going to plug these in here. And there we go. We have basically our difference equation set here. But it needs still a little bit work here. Now you can see we are dividing by tau. So let me just multiply with tau. That gives me this here. And you can see that we have x at k minus 1. Here's also a x at k minus 1. So let me just rearrange stuff here. So there we go. This is basically sufficient. We can use this set of equations here in order to use a for loop and to calculate the internals and externals of a closed loop connection here. So this is basically our simulation. This will be our simulation code. Now, how can we use this? Well, first of all, we need to acquire A, B, C, and D here, but that will be done using MATLAB. But once we have the sampling time, once we're using this fact here, we need to define a time vector here. Let's call it tau. Let's say up to 10, or maybe let's use 1 second for now. And then what we will do is we will start at a certain time instant. Since we are using the previous time instant here, what we will do is we will code a for loop here. But we'll start with the second element, because if I plug in k equals 2, then k minus 1 will be equal to 1, and all indices start at 1. So therefore, we should start at 2, where, by the way, k minus 1, if I is equal, or if k, let's call this k here, if k is equal to 2, k minus 1 will give us the initial conditions. Therefore, we're using the initial conditions here. And then this will be up to length t here. And we need to calculate these here. That's our basic code. Now this can be used for open loop simulation, since we have a certain input and a output here. Before I continue with this, let me comment this out. Let me just acquire A, B, and C, or calculate A, B, and C. So we can just directly use the data given here. It's 1, 15, and 20, TF to SS. Let's see what A, for example, looks like. There we go. Now this is a 2x2 matrix, which means that we have two state variables here, x1 and x2, and therefore we have the derivative of x1 divided by dt equals, let me use it, minus 15 times x1 and minus 20 x2. So this is basically the first equation, and then we'll have the second equation, which is just x1, and then of course we will have b, which gives us the following here. And let's see what C is and D is. So basically, Y is equal to 40 times X2. So this is basically the same model, but the expressions are in state space representation. And you can think of this as follows. Since this is a transfer function and it is in the Laplace domain, what you can do is you can just acquire the corresponding differential equation here. It will be a second-order differential equation, since this is a second-order transfer function. Therefore, you'll get a, in this case, linear differential equation. And what this is basically is we have just internal variables which help us in reducing the orders of these equations. Instead of having a second-order differential equation, you have just two first-order differential equations, and that's it basically. So we will use this here, and the fact that we have a 2x2 system will be important in a moment. So now this is, again, continuous time state space formulation, but we have to convert it into discrete. So there's a function called continuous to discrete, C to D, and it'll convert a certain continuous time dynamic system into a discrete time 1. But I've also shown you that we can do that by ourselves. So actually this A, this B, and then these C and D matrices are discrete here. So you can use C to D with the same sampling time and zero order hold method, by the way. Or you can also use the following definition. So we can do just define this. And BD equals tau times B, and that's it. CD will be equal to C, DD will be equal to D because they are static relations. So now, of course, when I define a new variable instead of this, what I can do is I can just use them here. So we have still a problem, and the problem is the following. X here is not defined. That's one of the problems. And there's a size compatibility issue here. AD is a 2x2 matrix in our case. Therefore, we should define a vector. And I've shown you that there are two state variables. Therefore, we have x1 and x2. So what we really should do, instead of doing this, is to define a kind of a matrix here. And in this matrix, we will have two rows, each row corresponding to each state variable, and then as many columns as the T vector has, because each column will correspond to the time instance. Now, if we define this, and since the output, and we're dealing with single input, single output systems, the output will be basically just 1 by length t or size t. So now I'll say we are almost done. What we still have to do is we should update the indexing here. Namely, we need all the rows, but column k minus 1. And since U is basically just a 1D vector, we don't really have to use all the rows and k minus 1. We know that this is a 1 row and length t column vector here. So therefore, I can just access k minus 1 here. But if I'm accessing x, I should use all the rows here. So here we again have all the rows. Kth column should be equal to the previous column times AD plus B times UK minus 1. So again, you're not responsible of this part. You might just want to need to use it, and that's it. Now let us also use CD and DD. And I guess if I'm not wrong, I can use this here, but just for the output maybe, in order to see if it's really working or not. Now, yeah, this should be good to go. So tau should be defined here, whereas we're using tau here. So let's go up a little bit. U, we didn't define U. Let's also do that. Use again, the input and output will be just a vector. So I'm using size t here. And we have basically y, x, and some other stuff here. So let us put in these here. So now in U, in Y, everything is 0 here. What else do we have? In X, everything is 0. And if you're applying step to a certain transfer function, you have to apply 1. Therefore, let's change zeros into ones and apply just one input to the system here. Now, here you can see that this still doesn't work, and the reason behind that is probably the choice of tau. So in order to have this working, we need to choose a small sampling time. So let's try maybe 10 to the power of -3 here. Hope that this works. Still not there. Now, what else could it be? Let's see, 40, 115. So times B, AD, K minus 1, UK minus 1, is equal to K1. Let's see. Still working. And then first element is 0, second. Seems like we have an issue here. We have to access. And sampling time. So let's see what AD looks like. Seems like we have still an issue here because since this is a discrete system, this should be in the unit circle, but it is not. Interesting. And why not? Let's see. What did we use here? In this part. Seems like we've directly used this part here with method stat. Let me again try with an even smaller one. Where's tau? Oh, this is wrong one. Tau. Let's even further decrease this. Hope that this one works. Still not there. Interesting. So let's take a different approach. Let's use C to D here. Maybe that has something to do with it. And we've used 10 to the power of minus 3. Yeah, this should basically work, but let's see. Now here, I guess we won't use that anymore. And here we need the sampling time and the method zero or hold. Let's see. Oh, it expects us to give it the transfer function, of course. Interestingly, it still doesn't work. We have this. I guess I know what the issue here is. So the output should be 1, and then we'll access it after. So this is probably the reason here. So finally, now it seems like the discretization that we've tried didn't really work, and I'm not quite sure why, but it should. Maybe I did forget about something. But we've used again MATLAB to acquire the discrete form and then all code. Now you can see that the last sample is not really working here. The reason there is that we are plugging in length k, length t into k, and we're assigning the last or one before the last here, so length t minus 1 in the output. In order to update that or get rid of that, what we should do is we should just replace repeat this one more time for the last element in the array. So let's do that. Now here we have basically our simulation, but we didn't use 10 seconds. So let's change the final time here and let's see if it's working, and it does. Now, of course, GS, ZPK, GS, we can see it has real roots and therefore we don't have any overshoot. It seems to be working. So now, of course, this is basically an open loop simulation code, the minimal open loop simulation code using a discrete model of the transfer function. But as you can imagine, we are not going to simulate the open loop. What we need to do is we need to use the controller, use the system, and create our own closed loop simulation here. Now, in order to do that, let me just look at the values. Should I copy this? Maybe we should copy this. So I just need KP and KI. Before we do anything, let's just design a controller here. So we define these, we design a controller, and then we begin simulation here. Now, let's run again to be sure that it does work. There we go. Now, what we need to do is we need to first of all create some extra variables here. One of them is the reference. We have a certain reference signal. We have outputs, and the difference should be stored in E here. So let's have zeros. And then we also need the integral of the difference between r minus y, because ki times that should give us the one portion of the control signal here. Therefore, let's define another variable. Let's call it q, which is the integral term. So the output of 1 divided by s. And basically, we have r minus y should equal to E, and then Q and E should be combined using KP and KI. That would generate U, and this U will be applied to the system, which is the case at the moment. So therefore, we have to first look at the difference, let's call it K minus 1, between R. So I'm basically directly implementing the relations here. But the only difference here is that it is discrete. Now here the reference is equal to 1. So therefore, at k equals 2, so the first element of y and the first element of r are subtracted, and we get the first element of e. Once that's done, what we need to do is we need to calculate the integral of e. So this should be somehow e dt. So how can we do this? So this part is a bit important. How can we take the numerical integral of e? Now, in other words, dq should be, dq divided by dt should be equal to e. Because if you solve this equation, you'll get e dt. And therefore, since I'm using again zero order whole method, what I can do is I can do this. Divided by tau should give me e. I've taken a difference and I've divided into tau, and I've equated e. This is basically an approximation here again. Now, if we have such a difference, what I can do is I can just multiply with this, and I'll get to this point here. Now here in line 49, you can see basically that we are basically adding up error terms to a certain sum. So Q is basically a sum here. It's summating all the error values. So therefore, this will be directly our equation here. Since we have tau, we should be good to go. Now we have the error, we have the integral of that. So why not calculate the control signal? And here we can use directly the relation Kp times Kp val times Ek minus 1 plus Ki times Ki val times Qk minus 1. That's it basically here. And what else? Well, this input will then be applied to the system, and then we'll get a certain output. And that should be it. So let's also repeat this one here, by the way. Oh, no, we don't really need to do that. What else? Maybe this one here should be repeated. And this one here. So there we go. Now let's first run this to see if we have a problem. Seems like it. Line 48. Of course, this is just a comment. This here. So let's see. Just comment this out. Now we are taking the difference here. But we should move this on top here. This should be it. Now let's see. There we go. Now, let's open this up. Let's try it again. Very good. Now, since I have all the internals defined here, what I can do is I can do the same part here. Let's repeat this part. Let's see if it still works. And there we go. Now, of course, there are some elements missing here. Let me see. What else do we need? We have Y. Seems to be working. Let's put it there. And EQ. Well, it should be it, actually. Yeah, of course. Now, as you can see, we didn't basically move that much from the previous point because we did already get this effect. But the difference here is that we have all the internals and we are doing this manually. So if you're just interested in the control signal, this has no meaning. But if you want to use a saturation element, which we will do in a moment, then this will help you out. Now, there we have a difference here. We can also include another value here, or vector, that has meaning, namely the integral of E. So it's possible to use that too. As you can see, now we have an additional vector here, or signal. This one here. And we can also do something else. Since we're looking at the control signal, what we might do is we might go ahead and use Kp val times E. This will show us the p-type controller part of our controller. So we can see the proportional effect here. Let's plot it in red. Of course, so let's assign a color here. There we go. Now we have the proportional effect, and we know also what the integral part is, so we might also look for the integral effect. So let's do that too. Let's have ki val times q, let's say blue. And there we go. Now we can examine the control signal a bit more in detail. And I guess 10 seconds is not a good simulation time because this was the open loop and we have settling time too. Maybe we should change it to 3 here in order to zoom a little bit. So where was it? Here. So let's have that too. And there we go. Now we have better figure here. Now here in the control signal, we can see that the red part is actually the p-type controller part. And the integral of E starts with 0 here. And as time progresses, the integral term increases here. But up to this point, we have such a big integral, it takes time to decrease this integral here. Therefore, it takes also time for the overall system to reduce the error to 0 here. And you can see that basically the p-type controller part is dominating at the beginning, and at the end, the integral part is dominating. So therefore, we can see that there's a blending between the integral part and proportional part. So you can think about the PID controller a bit different here. You can take into account that there will be derivative part, integral part, and proportional part, and they will all be acting together and will try to drive the system to the output. Now, again, this is not that exciting. Now comes the good part. Here in our question for today, we have to limit the control signal. Now that's the fun part. So let me do something here. Now simulation without saturation. Let's call it that. Now here, let me copy this whole thing and paste it down here. So this will be with saturation now. Of course, we don't really need to define these here, not this one here, but we might need X, Y, U, etc. For now, let's don't change basically the names of the variables, but if we need to, we'll maybe change them. So what will be the difference here? Now, if you're in Simulink and if you're dragging and dropping a saturation element, keep in mind that it will have an input and it will also have an output. Therefore, we will have two different control signals. One of them will be the raw control signal. The other one will be the saturated control signal. Therefore, we need to define another control signal here. Let's call it U-sat, which will be basically the output of the saturation element if the input is U. Now here, once we've calculated it, it will be very easy to saturate this U here, this control signal, because if U at this time instant is bigger than a certain limit, let's call it U lim, and let's define this U limit. For now, let's define it 0.7. So if it's greater than U lim, what we need to do is we need to assign U sat k minus 1, which will be the output. The output should be equal to this limit here. Otherwise, if the U signal or the control signal at this time instant is less than minus U lim, then again, it should be equal to minus U lim. Otherwise, U sat will be exactly U. So if we're between the limits, in between the limits, then we're here. If we're outside the limit, if it's a positive value, If it's, for example, 0.8, then we'll saturate the output. So the control signal will be 0.7 and nothing more. If it's lower than minus 0.7, then it will be 0.7 again. But between those two values, it will be whatever it should be. So then, instead of applying U to the system, we will use U set here. And I guess, again, U set should be also for this one here. Now, it seems to be all right here. Let me, by the way, get rid of all the unnecessary stuff. So let's have the let's have the control signal and the output, and that should be enough. So 2 by 1 the first one, 2 by 1 the second one. That's it basically. So let's also save them like that. There we go. Now, with saturation, I'm just going to get rid of all the stuff here, and I'm just going to use another, let's say, blue color. And that's basically it. Now, do we need anything else? I guess not. So let's try this out. Seems to be all right. Of course, we have to plot something else, and that's basically, let's have this, and let's have this. Now, keep in mind, U is not the actual control signal applied to the system. U set is the actual control signal applied to the system. Now we have an interesting thing here. Now, the dashed line here shows us the generated control signal. The controller generates this signal. And the actual control signal is the blue one. And you can see that the rise time, the settling time, they did change. And I guess we can also include something else in order to analyze it a little bit better, namely the integral maybe. So let's again change it to 3 by 1. Let's also plot the integral, because that might be important. So therefore, x2 and 3. So 2, 3. There we go. So now let's run it again and see what's really happening here. Now, this phenomenon is called windup, integral windup. So, and the reason for that is the following. Now, look at the control signal here and look at our applied control signal. And by the way, you can also see that the integral of error is huge in this case. So what happens is the following. The system applies a certain control signal, actually wants to apply a certain control signal, but it is over the limit. So therefore, it becomes cut off. Therefore, we have a certain maximum value that we can apply, and that's it. Now, as this is the case, the controller gets more and more aggressive because it tried to apply a certain value to the system as an input, but it didn't get the result that it was expecting. Therefore, it increased the effect here, so it became more aggressive. At a certain point, even though at exactly this point, even though we are not, or we don't have to really apply values higher than 0.7, we still can't. And the reason here is that the integrator part grew so much that we couldn't, or we cannot apply a small control signal. Now, here, the integrator is basically messing up the behavior here. The controller cannot perform well because the integral part grew too much. And it, again, takes some time in order to decrease and get rid of this huge sum that is accumulated in the integrator here. Therefore, even though we are not outside the limit, we have this integral part, and it's causing some problems. Now, what should we do? Well, basically, ideally, what we might expect is that during this portion here, we should maybe apply this blue control signal, namely the limit. But after this point, why are we applying still this huge control signal and it is becoming cut off and we struggle? Ideally, it should follow this black line here. So it should just apply the amount that is needed here and it'll settle down, basically. But that's not what's happening here. So how can we solve this problem? Now, in order to solve this problem, there are two ways, or two most used ways. There are maybe multiple ways. And one of them is to just disable the integrator during saturation. So you can detect if you're saturated, if you're above or below the limit. Therefore, what you can do is you can just turn off the integrator. So what we try to do here is we are going to behave like a p-type controller during saturation, and then we'll activate the integrator outside or between the limits. If it's between the limits, then we'll again turn on the integrator and we'll apply PI control. So it seems like we don't really have to use a PI controller during the saturation because we cannot even use any controller because we are just applying the limit. This is not a controller, this is the limit. Therefore, let's copy and paste this part again. But now the wind-up prevention part is going to be included. Therefore, we might call it with anti-windup, since this was caused, and we'll just get rid of the effect here. Again, we have a certain limit. We don't really have to assign this anymore. Now, what we can do is we can just define a flag. For example, is saturated, and then just define it false. And once we are entering this if case here, is saturated should be equal to true. And this is also the case if we enter this here. Otherwise, we should set it to false because we are not between, we are in between the limits. So it should not cause any problem. Now, this is the flag determination part. But what we should do is we should basically, because this is the integrator, disable the integrator. So we can do the following. If it's saturated, do something else, do this, and then end. So what should we do here now? Since in this case, it should take the integral, but in this case, if it's saturated, the integral should not grow. So what we can do is we can just copy this here. Instead of e, let's say 0. So we're taking the integral of 0. So we're adding 0 to the accumulative sum. Therefore, the sum should not change, and the sum during saturation should not increase, because that was exactly the problem here. If this signal, because this is dominated by the integral part, if this integral part does not grow this much, then this effect will not be that worse. So now, since we need to determine if it's saturated, we're using the saturation block here. And if it's saturated, we're adding 0 to the sum. If not, we're adding basically the error to the sum. And that should be basically it. Let's assign a new color. Let's call it red. And let's see what happens. So here, we again can see that we are spending some time in saturation, but the effects are not that worse. You can see that here, the calculated control signal is way better than the wind-up case. And if you zoom in a little bit, you can see it stays just 0.78 seconds in the saturation, and then it'll just behave like it should be. And we can also see that the integral does not grow, and then it starts to grow, and it just does the job here. And here we can also see that the settling time is again almost there. Maybe the rise time is not really according to the design criteria, but we can also conclude that this is maybe because of the fact that we have a certain control limit and we are expecting too much of the system in the closed loop, because this controller can only do this much if we have a limit 0.7. Because it can only apply this. It cannot be behave faster because the control limit, the control signal limit, is too low. And you can see that it takes almost 1 second to rise to a certain, maybe 0.8 seconds to rise to the certain value. And then but we can meet the settling time requirement, so that's in our thing here. Another strategy is to, let me copy it again. Another strategy is to do something else. Anti-windup 2, let's call it 2. Now here, instead of having a flag and determining this, let's get rid of this. We can do something else. Now, let me get rid of this and this and this. So instead of doing this, what we can do is we can tell the integrator that there's a certain difference between the applied control signal and the calculated control signal, because there is a difference. So if we subtract this difference, which is too much in this case, from the integral, then we should be safe. So instead of taking the integral of E, we are going to take the integral of something else. Namely, we are taking away the control signal part, K minus 1, but we are adding the saturation part. So we try to compensate for the fact that we have a certain saturation element. And we try to do that by telling that I gave you too much of a sum. Let's just take this away and put back the actual value. So in this case, for example, if we calculate 20 here instead of the control signal and apply 0.7, we are subtracting basically 20 and adding 0.7. So we're correcting the sum during the saturation here. So, of course, it raises a question here because we have K minus 1 here. We need the control signal K minus 1, but we are calculating it here, down here. So we don't actually know the value at this point. Instead of doing this for K minus 1, we might just have a certain delay here, just one sample. And instead of doing this, we might go ahead and look for the previous control signal that was applied and the previous saturation value that was applied. So therefore, in order to have this working, what we need to do is we need to check for k greater than 2. Else, because k minus 1 should be equal to 1 at least. If k is equal to 3, that's the case. So therefore, we need to include a certain if. Now, if it's not that, maybe we can skip this for one sample, which is not the end of the world. So therefore, this should be good to go. Now let's see. Yeah. Now let's assign us another color here. Let's use magenta. Now, of course, it gets a little bit crowded here, but we can see that that also solves the issue here, which is a bit different because we have a delay element and then we have, we are basically subtracting the difference from the control signal from the error itself. So therefore, there's a bit difference. But you can tune this parameter because this is kind of a feedback loop on its own. Therefore, you can assign a certain gain to this, but I'm not going to bother with that. So what we can see from here is that if we have an integrator in in our control loop, and if we have a saturation, then it is practically dangerous to use such a control setup. And the reason behind that is the following. If we are in the saturation limit, or if we are applying the limit, then the integral is a ramp function. Therefore, it increases too much, and it increases with time, proportional to time. If we are in saturation for 10 seconds, then it will be 10 times the error value. So it's too much of a difference. We have to compensate for that, and there are two ways of doing that. We might just turn off the controller, switch off the integrator, turn it into a p-type controller during the saturation. We can live with that, you can see. And or we can just subtract the difference between the saturated control signal and the actual calculated control signal in order to compensate for this behavior here. Now, let me also remind you that if we choose the limitation here, let me find it here, ulim. So if we change it to a higher value, let's say 1.2. Let's look at here. We have basically almost 2 as a value. If I have a higher limit, what do I expect? Well, basically what I expect is that it should not saturate this long because you can apply more control signal. So if I change the limit a little bit, we can see that the control has more freedom because of the limitation, and it behaves almost like the actual control without any saturation here. And if we decrease this limit, for example, let's put in a harsher upper limit like 0.4. Let's see what happens. You can see that the behavior did change. And the reason behind that is we need a certain value for steady states. Now, this is the integral. This is the control signal here. And if I zoom in, I can see that 0.5 is necessary to track this input. But since the limit is below this value, since it is 0.4, it never reaches the reference here. It cannot track it because there is not enough control signal here. So therefore, it is important to look for the control signal limit. Let's put it back on to 0.7. And it is also important to choose the time domain specifications accordingly, because in terms of rise time, this is not a good choice, not a good specification, because we are not able to meet it with this control signal limit. But if we have, for example, 1 second as the rise time specification and 2 seconds as the settling time specification, then we might get a better output of this. Now, we should also take into consideration that if we do such a thing, we might slow down the system overall a little bit, which is a good thing if you are trying to hit the limit here, because we should avoid the saturation limit. During the limit, we have basically no control over the system at all. Now, for systems that are not really that crucial, this might be not an issue. But there are certain systems, for example, for the road handling of a car, we don't really want to lose control in such cases. Now here, it might be also not a good thing to lose control when you are in the saturation limit. Yeah, that is basically it. Now, did we have anything else? And then there's a comparison, but yeah, we've already talked about this. Now, to conclude, we did design a PI controller for settling time 1.8 seconds and rise time 0.3. Now, we've looked at the control signal, and we've seen that we can use basically the manipulation of the block diagram in order to look for the transfer functions that will give us the control signal, the error signal, or the output. So these 3 transfer functions are really important. So note that. And we've also seen that we might need to limit the control signal with certain upper and lower bounds. We did that exactly here. But in order to simulate this, we might use Simulink or the code that we've written down here, which was based on the difference equations of dynamic systems. We needed to convert the continuous time transfer function into a discrete time state space model. Once we've done that, we've used basically x dot equals ax plus bu and then y equals cx plus du. Other than that, you should also note that we have implemented a digital PI controller. This is not a continuous time PI controller. This is a digital PI controller. We've used the P gain and the integrator gain, and we've just used numerical integral and the error itself. This is a digital controller. So this can also exemplify the implementation of a controller, because we might have a circuit, a DSP or a certain digital circuit that calculates this whole stuff. It uses the measurement and it just generates the control signal and applies it back to the system. So this could be the case. But here we don't have the hardware in the loop. We have just a simulation in the loop. So therefore, that's also important. And we've seen that using this approach for simulation or Simulink, it is possible to reach the internals of this closed loop, and we can then manipulate the control signal. By the way, I've shown you the saturation element, which is a nonlinear element, by the way. So our overall closed loop is not linear anymore, by the way. You can also implement the slew rate here by using use u minus uk minus 1 minus uk minus 2, another back difference maybe, and then you might limit that difference to a certain value. Then you will implement a slew rate here. But I didn't go into detail because this is already too much code and it might become out of control. Now, then we've seen that there are two basic anti-windup strategies. One of them is to switch off the integrator during saturation. The other one is to compensate for the fact that we are applying a different control signal than we've calculated. So take this difference, give it to the integrator, and hope that you will solve it using that. Now that's it for this week. If you have any questions, feel free to ask. I do what I can. I just forgot to give you this one here. And that's basically it for this week. Now, do you have any questions? So, Flaman.